Good morning and welcome to our CMCC webinar of today. This is in a way a special seminar because, well, first of all, it was arranged and prepared very quickly, and this is due to the fact that we had a short time to prepare this, and we were working under some severe constraint. But today is an important seminar. This is part of the CMCC seminar series. Let me say a few words about CMCC before starting the seminar. Oops. Okay. CMCC is a foundation that is working with, is dealing with studying climate change from the design of the numerical models to the impact analysis and economic and policy analysis. And everything is kept together by the usage of quantitative methods, usually numerical techniques, that are supported by our computing center that is a tier 1 class computing center located in our headquarters in Lecce in the south of Italy. That at present is a system that is in the petaflops range. We're buying a new one soon that will double our capacity. That's where we are doing our simulations and data analysis and so on. Our mission is written here, is to investigate and model the climate system and interaction with society with the objective to provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation mitigation policies. And of course, also to develop foresight and quantitative analysis of our future planet and society. That's meaning that we're also very interested in predictions, investigating how far we can predict, what we can predict in our interconnected global Earth system that includes not only the natural environment, but also the social and economic environment. We are organized as a network, so we have divisions, research division in these places in Italy. But the sites are more or less specialized. So Bologna, for instance, is specialized in computing and model atmospheric and oceanic modeling. Venice and Milan are specialized in economic and policy analysis. Viterbo Sassari in ecosystem and agriculture. Caserta is mostly concentrating on regional climate modeling and impacts on land. In Lecce, we have our headquarters and a number of divisions that are working with computing, scientific computing, ocean predictions and applications, and our organizational center. These are our research division. We're at this present time, we have 10. That's basically try to cover the kind of fields that I've mentioned you before, and I won't spend much time on this. The topics we're covering, as I said, are trying to address all the various aspects of the climate problem. Try to start from the basic science into the social and policy relevant aspects. We are very active in outreach. We have a very active communication group. We're a number of publication events. We're very much integrated with education because a number of universities are involved in our foundation. University of Bologna, University of Ca' Foscari in Venice, University of Salento, University of Tuscia, University of Sassari, and the Milan Polytechnical Institute University. So we are working closely with PhD programs in many of these places, in particular with University of Bologna, University of Venice. We have strong cooperation with their PhD programs in climate science. A few words about how it's going to work. Your audio and video will be deactivated, but there will be a Q&A section open through the during the seminar. So you can either write in the Q&A section or you can raise hand, and then at the end we will have a discussion. So let me finish with the fact that these things will be recorded and uploaded to our YouTube channel. And that's our website. So if you have an urgent desire to know more about us, you can go to the website. And now let me stop sharing And let me say a few words about today's speakers, if I can grab them here. So today we're very fortunate to have with us two leading experts in the field of quantum computing. Quantum computing is something that you must have all have heard of, I'm pretty sure, and you probably are very curious to know how, or probably must ask yourself in which way these things can be used by us. The first speaker will be Federico Mattei, that has been involved in designing and developing innovative project at IBM Italy, especially in the financial service sector. So he's a very important person. He knows about money. And he's been working with quantum computing and application of quantum computing on the fintech kind of application. He's a physicist, a theoretical physicist. So you have to be careful what you say to him because he actually understands what you're saying. And he's not only a theoretical physicist, but like many physicists, he also has a knack for something else. So he's a master in business management. So he's really a crucial person. And the other speaker today will be Michele Grossi, that is working in the cloud team, hybrid cloud team, and is quantum technical ambassador at IBM. He's also a theoretical physicist and has been working on how to use the latest technology in application from machine learning to quantum computing. And is very well. He's been selected as one of the top 30s, under 30s in 2019. So I'm not sure if he's under 30s right now, but he's still a very bright person. That's what I understand. So we're really looking forward to these talks today. And just a few words. We've been listening to the raging debate about quantum computing in the press and in the scientific community for a while. But the main point is that we solve differential equations. We solve time marching differential equations. And so the question is in which way the quantum technique can be used in order to make our job faster, more competitive, and basically beat all our friendly competitors around the world. So we're waiting for you. Thank you very much.
Thank you very much, Professor Navarra. Thank you to you all that are connected today. So let's begin with the sharing. Here it is. Me and Michele, we are IBM Quantum Ambassador in Italy. So this role is to bridge between the country and so universities, research institutions and enterprise with IBM Research, which is a division of the IBM Corporation in the US, which studied quantum computing since the beginning, so since the early 80s of the last century, and that 5 years ago decided to put on the cloud, in the internet, available to everybody, quantum computers to begin to study the application field. So our speech today will introduce you to this topic, will disclose you all what is available on the web to you to use these kind of technologies. And at the end, Michele will also introduce you to some application that we are beginning to discover on this technology. But we are on the early phases of this technology. So the activities that we can propose to you and we propose to all the people and the institution we talk to in this period is to study together and to understand together the real potentialities of this technology applied to you. So it will be a joint research in order to understand which are the real application in your field. So let's start with a really quick introduction. The first slide I put in this presentation regards the future of computing. And IBM Research in the future sees mainly three kinds of computation approach. One based on mathematical laws, in particular logical laws, which is the information theory that we use every day based on the bits. Together, so complementary to this kind of computation, we have the artificial intelligence system that we are learning to use in these years, and which works together with the informatics that we used to use last years. And in these days, we are beginning to insert another kind of approach to computation, which is quantum computing, which is based on physics laws, in particular quantum mechanics. So in the future, we see a collaboration between these three kinds of computational methods. And today we will introduce this last one, which is very narrow in these days. So it's not 1/3 each kind of computation as we see in this chart, but it's just very narrow. But we are beginning to study and to enlarge this slice of the computation of the future. So the motivation, I think that most of you knows the motivation which we are introducing this kind of computation. We know that the traditional model, so the von Neumann architecture of computing, fails to solve several kinds of problems, in particular the exponential problems which rise the time of computation exponentially with the complexity of the problem. One of the problems that we fail to solve using classical computer are molecular simulation. Here is just an example of caffeine molecule, which is quite a mid-size molecule. And we know that to model precisely, of course, without any assumption and reduction of the model, we need really a lot of bits to simulate it. So 10 to the 38, which is, if we think one bit as one atom, something like 1/10 of the Earth. So to compute with our current model the exact solution of this molecule, we will need to build a second moon just to do this computation. Another kind of computation which is very popular and we really know how it works is the factorization versus the multiplication activities. We know, of course, these two operations since the primary school. And we also know that rising the number of digits of this number, the current computational methods easily do the multiplication activities, but it's really hard to do the factorization one. So we leverage on this kind of asymmetry of this computation, for example, to do cryptography. So these are just two examples, but we know that there are a lot of problems that we struggle to solve using classical computation, so the computers that we have in front today. That's why at the beginning of the 1980s, there was an important conference. We have the anniversary of this conference in the first days of May of this year. There were 40 years since this conference. In this conference, they begin to debate the physics of the computation. You can recognize several scientists which build the theory of quantum computation. Between them, of course, we can see also Richard Feynman in the back. And let me start with Richard Feynman, who stated, and this statement was taken to be let me say, the beginning of the studies of quantum computation. He stated that nature is quantum mechanical, and so we cannot simulate it using classical methods. We need quantum computational method to simulate quantum mechanics. And that's taken as a starting point, as a first idea, to build this new theory and also to build these new quantum systems. Maybe all of you knows the main difference between classical computation and quantum computation. It lies at the very basics of the computation. So the classical bit, we know it can be in two classical states, 0 and 1. And using this bit, a lot of these bits, we can of course reproduce text, videos, images, and all the rest, and we can do computation on them using logical gates. In quantum computation, the traditional classical bit is replaced by a quantum bit, which is called qubit, and it leverages on the superposition property of quantum mechanics. So a quantum bit, which has two classical states, 0 and 1, can be put in superposition, and so can be in a state of combination with complex coefficients of these two states, 0 and 1. And since we are going to measure it, it will remain in this very rich state and very rich amount of information inside it. It can be represented as the surface of a unitary sphere where 0 and 1 are in the North Pole and in the South Pole, and the state of the qubit can be represented as a point on this sphere. So you see how much more information we can put inside a single qubit. Of course, at the end of the computation, when we do computation on this bit, on this qubit, we are going to measure, and so the result will remain a classical series of 0 and 1. But if we are able to leverage, using our algorithms during the computation, this large amount of information, we will obtain results that cannot be obtained using a classical computer. A second property that we use, taking it from quantum computation, is the entanglement. So we are able, inside our quantum computer, to put in entanglement 2 or several qubits. The entanglement property of the quantum mechanics allow us to do some strong correlation between these qubits, and so perform inside our algorithms a really huge amount of computation and the possibility to span between a vast space of states. Between them, we can then focus on the result. So all the problems regarding optimization, simulation, and also neural network seems to be good candidates to be solved using this kind of computation. So let's turn to the technological parts. After nearly 40 years of theoretical discussion on quantum computers, because we know the property that it should have, but we do not have real quantum computers. Inside laboratories have been developed several computers with, at the beginning, 1, 2, or a few qubits. And in 2016, IBM research decided to publish on the web, available to everybody, the first quantum computer with 5 qubits. Today, we have the largest number of qubits in a quantum processor is 65, which is this one. And we also published at the end of last year this roadmap that you can see now on this chart. We are committed to pass the number of 100 qubits this year. We will have this Eagle processor of 127. And the most important milestone will be in 2023, when we will have a 1000 qubit processor. Having this kind of processor, we think that we will reach a quantum advantage. So for the moment, there is no advantage to use a quantum computing together with a classical computer to solve real problems for the industries and also for the research. So in this period of time, we are developing application with toy models, with simple environments. For example, we published the simulation on beryllium hydride, of lithium hydride. So all molecules that can be, the basic state can be easily calculated using classical computers. But we do this publication to simulate this kind of molecule using quantum computers, and we know that as far as we will have enough number of qubits inside our computers, we will be able also to simulate the molecules which we are not be able to simulate using classical computers. So all the efforts that we are doing now is to building models that we will leverage as soon as we will have enough number of qubits inside our quantum computers. We are also building new fridge. Maybe you know that our quantum computers are based on superconducting materials. So they work at very cold temperature, 15 nanokelvin. For the moment, the dilution refrigerator are smaller than this one, but we are working on this kind of cooling technologies in order to host also technologies of 1000 qubits, and maybe also in the farthest future also 1 million of qubits, which will be required to solve some kind of very complex algorithm. For example, the algorithms which are behind the factorization, so the Shor algorithms, for the one that you know, this algorithm, which has been published in 1984, and which allow us to factorize large numbers using quantum computers. An important value, an important measurement that we propose to the scientific community to measure the power of a quantum computer is the quantum volume. We have not to judge quantum computer just by the number of qubits. The number of qubits is very important because it represents the amount of information that we can put inside the quantum computer. But we have to take in account also all these other quantities. For example, the crosstalk between the qubits inside a processor. They tend to put in entanglement one each other, also without our control. Of course, the coherence time. You know that the quantum state remain in a coherence time just for a short period, and we are trying to enlarge as much as possible the coherence time, which will allow us to do a deeper kind of algorithms. So for the moment, we are binded for the amount of operation that we can do in a single algorithms by this coherence time. And we have also all other kind of errors that we can do inside our processors. These are the first processor that we built. So the first one are 5 qubits processor with different topology. Of course, they are planary topology. They are put on a plane. This is a 16 processor, and this is the evolution of our 20 qubit processor. Each point is a qubit, and each line is the possibility to put in entanglement one each other. In the first release, they are deeply connected, but we have to face the problem of crosstalk. So we arrive to this kind of topology, which is also used for the 53 Rochester processor, which seems to be the best compromise between connection and error correction. So this is also very important, not just the number of qubits, but also the noise management. we are working on the processor. These are all names of processor of the 20 qubits one. So you can see the Austin is the first one, the more connected one, and the Almaden, Babling, Singapore, the latest one. And here you see the Austin processor, which have a vast amount of gate errors. So the errors that I do putting gates in front, so operations in front of the qubits are very large, and we are pushing back to the 1% the errors in this new kind of topology, working not just on scaling the number of qubits, but also on managing the errors that we do performing computation. Looking at this quantum volume component, we can do a comparison between the power of classical computers in the early 60s of last year, which is the Gordon Moore law for classical computation. And we see that each year we double the quantum volume of our computers. So this picture, together with our roadmap of the enlargement of the number of qubits, are very encouraging and tell us that we will probably have in a couple of years quantum computers that will be able to reach a quantum advantage, and so that we can really use during our research and industrial activities, not just for doing some experimentation, but also to really work on the production, so on the real activities. This is my last chart in order to show you how you can program quantum computers, and then I will leave the stage to Michele that will begin his part with a short demo of what you are going to see in this short video. So to program a quantum computer, an IBM quantum computer, which are all on internet, so all of them can be used from your laptop on the cloud. So you can start doing some programming, and we will see how in a few seconds. It will go on the cloud, and it will be transpiled for a quantum computer, and it will be sent on one of the 30 quantum computers that we put on the cloud available to the ecosystem, and the result will return to your laptop. In particular, this is the simulation of the lithium hydride, the energy states of the lithium hydride, which we published on the cover of Nature just three years ago. Of course, I repeat myself, this kind of computation can be easily done using classical computer, but the very important point is that if we can do this kind of computation having this few amount of qubits now, we think that we can manage using this kind of algorithms largest kind of molecule as far as we will have a largest amount of qubits. So this is my first part, and I'm closing my first half of the speech. I don't know if there are some questions.
Yes, so maybe Federico, we can use this switching between you and me to answer the question. I will read the question, then we can decide who will answer. So the first question is from Carla, which said, what is the need of resources and energy in production and use situation compared with actual computers? So I would say that this is the, let's say, the question regarding the energy consumption of this infrastructure of this quantum computer. And I would say that, as you shown in the previous slide, also with the bigger refrigerator that we lost more than thousands of qubits, of course, the biggest consumption in terms of energy is related to the refrigerator part, because we use a mixture of helium, so helium-3 and helium-4, the two isotopes. And so this is let's say, the biggest part in terms of consumption. But the funny part, let's say, the good part is that the cost does not scale linear with the number of qubits. So in the same infrastructure that hosts today, let's say 50 qubits will lost more than 400 qubits. So that's a good way of managing these resources, but we don't have a clear comparison up to now to that. I don't know, maybe the second question will be part of the second part, because in which way quantum computer could help concretely to solve urgent problems like climate change, biodiversity, and other planet boundaries. I don't know, Federico, if you have the receipt here or...
I think that the answer to this question lies in the collaboration between you and us in the
Yeah, no, I think that it's better to listen to the next presentation, because some of this question I think we'll find some of the answer in the presentation. So maybe we should go on with the presentation, and then we can come back to the question answer at the end.
Okay.
Yes, sure. I'm starting sharing my screen. Let me know if you can see it, I hope. So basically, I'm sharing the IBM Quantum platform. So this is the web portal that we published the latest part of 2016. So it's almost 5 years that we provided for free access to real quantum computer. Everyone can sign into this platform, and here you can really play and learn things about quantum computing. Before looking at what we can do, I am showing you the platform and what are the resources that you can use. Of course, there are a lot of documentation here in this part where you can, let's say, understand how the platform is structured. And in this part related to services here, you can see that there are a lot of information. The most important one are the system tab here. In the system, we have the collection of the current quantum computers that are available. Some of them are free that are available to everyone, the one that has not this lock here. So every processor from the bottom part. Each processor has a different number of qubits and a different quantum volume, so different performance. So they can range from 1 qubit to 15 qubit with different quantum volume. If you click on the processor, you will see in real time the status of the processor. So how many people are using the processor, what is the topology of the circuit, and the properties of each qubit in terms of different figure of merit, of different properties like T1, T2, that are two physical parameters of the qubit itself. And at this point, I would like to answer to the latest question about the topology of the circuit and how the software will compile our algorithm. So of course, we developed in this year an open source code to run a quantum computing algorithm. The software is called Qiskit, and is part of this distribution, and you can install it on your computer. It's a Python package. And of course, according to the algorithm and according to the hardware where you want to run your algorithm, the compiler, so the software, arrange the algorithm at different levels. So you can manipulate this part, or you can leave the software to help you to solve the algorithm according to the topology of the circuit. So there is a sort of optimization about the property of each qubit and the connection between those. On this platform, I can run real quantum algorithm in two ways. The simpler one, or the simpler one is called Composer. In this way, you have this graphical interface that represents different number of qubits, where you can drag and drop the gate, the quantum gate on the platform, and then you can have the corresponding Python code on the right part of the slide. So this is also useful for people that want to understand how Python is working related to the quantum algorithm. All of these gates are the standard Clifford gate that are part of quantum computation, and you can also have more general gate. You can apply in the end the measurement operation, and when you are ready with your algorithm, you can, let's say, set up and run your circuit, selecting the hardware where you want to run the algorithm. You can choose among different quantum computer chips, but also you can also choose among different simulators, so you can benchmark your result, and then you can collect different algorithms. On the other side, you can also use the lab services. This is a virtual environment that create for you a Jupyter notebook. So here you can run a Jupyter notebook algorithm. You can create a new Jupyter from scratch. You can import your Jupyter notebook, or you can start from the lot of tutorials that are available on the platform. So here I'm showing you a variational quantum eigensolver, where there is a sort of introduction with theoretical understanding and the definition of the algorithm you will see. And then there is a lot of possibility to define your mathematical equation, and also there is the part when you code for real on the quantum computer. So this is a Python distribution that uses Qiskit as one of the libraries to, let's say, interconnect with the quantum computer. As I said, you will find a lot of tutorials here. They are divided in different industry scenario: optimization, machine learning, finance, Qiskit nature, so a combination of physics and chemistry, and many other tutorials. So there are a lot of information here. So my suggestion really is to sign in and try to use as much as possible all the information that are already provided in this part. I will continue the presentation from Federico, because in this second part, I want to focus more on the developer ecosystem. So how we can really code a quantum computer, starting from the basics part, so more the physical related one that we call kernel developers. So here we understand that are people that are very keen and very passionate about programming a quantum computer from the qubit. So they want to manipulate the pulses of each qubit, the level of the excitation, and want to tune some of the parameters. But then we want to build also algorithm. So maybe we want to use a higher level point of view of programming. So in this case, we will use something that is already provided by the people working on the kernel side. And here we use the algorithm developer part to build, let's say, subroutines of quantum algorithms. So people here are concentrating on the mathematical part, on the creator of the operator of the unitary transformation that are part of the general quantum algorithm. When this part is ready, we think that also quantum computer can be used by other people apart from physicists as mathematicians. We have a lot of developers that are very good at coding classical computer. So we want a sort of frictionless developing of quantum computers. So in this case, also people that are used to program classically with the Python on different problems can use also quantum computer, because they can use the subroutine created by algorithm developers and kernel developers and adapt their classical algorithm with the quantum part. So in this case, the definition of a general algorithm, like an optimization problem, can be transparent with respect to a quantum computer. So we can use the standard libraries for classification in machine learning or for optimization, for example, and some of the subroutine inside this algorithm can be substituted with the quantum part. And so everything becomes transparent with respect to a general programming code. And one of the most important features that we introduced this year in the Qiskit coding part is the fact that we need a dynamic circuit, because we want to, let's say, establish the connection between our computer, our classical infrastructure, and the quantum computer, but we don't want to waste time waiting for the signal that goes from our computer to the, let's say, generation of the algorithm and execution of the algorithm on the quantum part. So we define this define this dynamic circuit as a way to remove this latency, and we let the quantum computer and the classical infrastructure that is located beside the quantum computer to perform all of the iteration of a quantum algorithm. This is simply because quantum algorithm in general are given by a probabilistic distribution. So in general, we need to run many times an algorithm to reproduce the probability distribution. And because of that, this iteration can be done very efficiently on the backend side, so on the part where the quantum computer is located. And in addition to that, a lot of quantum algorithms that are used today are called variational algorithms, where there is a strong interaction between classical and quantum computer, because quantum computer performs some quantum operation like the expectation value of some physical measurement variable, and then the classical computer is used to optimize some parameters of this variational circuit. And using this dynamic circuit, we can move all of this backlog in the backend part so that everything becomes very fast. So this was a very cool introduction this year. And because of that, we saw with Federico the definition of the roadmap for the hardware part, but we can really understand that just the hardware roadmap is not enough to build a quantum computer from a full stack point of view. So in addition to the quantum roadmap that now you can see it in the bottom part of the slide, the idea is that we are building also the middleware and the software roadmap for this development in the future. So what we build now are quantum circuit, and this circuit will be built in Qiskit runtime. So we will develop, and we are developing really this runtime that are a combination of quantum circuit and dynamic circuit together between classical and quantum interface. And on top of this, we are building really a Qiskit application module. So as I said, the idea is to have a frictionless module that everyone can use, so that everyone can connect to our platform and write very few lines of code to create an algorithm that is suited for natural science, finance, optimization, or machine learning. And to do that, we are building all this intermediate middleware layer. So pre-built quantum circuit, pre-built quantum algorithm plus high-performance computing, and advanced control system. And you will see that by 2023, this full stack computation will be ready, and we will have really quantum module services that can be used. The main application that we find today in quantum computer, that we already find because we have published so many papers in those fields, are simulating quantum system. And here, of course, we have quantum chemistry, material science, and high energy physics. We have artificial intelligence. This is a really big hat because we know that artificial intelligence comprises a lot of things. But the real contribution of quantum computer, let me say, is that we have some subroutine inside artificial intelligence application that can be accelerated with quantum computer. For example, in machine learning, or for example, in visual recognition and so on. And then we have an important pillar given by the optimization and the use of quantum computer as a benchmark to what is the well-known classical method to do simulation, that is Monte Carlo. And here we see a lot of application in finance, for example, portfolio optimization, risk analysis, but also we have a lot of application in the optimization field. So for logistics, for travel and transportation, for energy and utilities. Now I will spend really 5 minutes in showing some of examples coming from those different application fields. First one is quantum machine learning. So here on the left part, we have a collection of several papers that we publish on this topic. And these papers are published as a joint work between IBM Research, and IBM partners. So people that are working together with IBM, so industries or university of research center. And here we have a collection of what is quantum machine learning. So the usage of quantum computer for classification problem, for supervised or unsupervised learning, and different applications. So for example, in high energy physics, we have the usage of quantum kernel method that are a quantum version of the well-known support vector machine. And then we have some more theoretical publication regarding the structure of this quantum algorithm, and where those algorithms shows a sort of advantage with respect to classical case. Then we have some application in physics. So here I'm showing an example of the definition of lattice field theory with quantum computer. That's a really important, very important case, not only for quantum electrodynamics, but in particular for quantum chromodynamics, when we use lattice and quantum computer to compute to define the evolution of a system. So here we discretize all the field, and we define several operators, and we can define the dynamics of the system on the lattice. And we show how quantum computer can scale in terms of resources and in terms of mapping of different objects. Of course, quantum computer algorithms are based on spin formulation. So usually in those kind of algorithms, you see an important part of mapping your original problem, in general, your Hamiltonian, in an Ising Hamiltonian or in a spin Hamiltonian, where we can use quantum gates for those kind of digital computation. Another example is related to the finance, but this can be extended really for general optimization problems. So we have a paper about quantum algorithm for mixed binary optimization. This has been applied to transaction settlement, a well-known problem in finance, but the real result here is that we have an extension of the usage of mixed binary optimization problem to continuous variables, so not only to binary variables. So that was a really interesting part. And again, here the root part of this publication is the way we map the original problem to a sort of Ising formulation, and we exploit all of the quantum properties, and so all of the quantum properties related to quantum computer to solve this optimization problem. So we exploit superposition, entanglement, and we can solve very easily this part of optimization. Another nice example, again, in the finance. Why a lot of examples in finance? Because the finance industry starts very soon investing in quantum computer in terms of resources, in terms of people that are studying this topic. And here we have a comparison between what is the classical method that we use to study the risk analysis. So we use Monte Carlo simulation that, according to different number of samples in your portfolio, elaborate a sort of estimation for the risk in the investment. And we developed a quantum algorithm that is called, the root part of this algorithm is called quantum amplitude amplification, that shows a quadratic advantage in terms of estimation error or in terms of convergence of the algorithm itself. Latest one is a completely different topic. Here we see a collaboration, for example, between IBM and ExxonMobil, where we developed for the first time on a real quantum computer the observation, the calculation of thermodynamical variables with chemical accuracy. So we developed this algorithm that is sketched here on the right part of the slide with a, let's say, a sequence of gate, a single gate, and entanglement between the qubit that allows you to calculate accurately the thermodynamic observables of a problem. And that is very useful when you are studying new object, when you are investing to understand the evolution of some new materials, and a lot of the investment has been done also for the study of batteries. So when you are able to study some thermodynamical observables, you can study different complex scenarios. And for the chemistry part, we have already some interesting publication in the study of protein folding. Protein folding, of course, is a very complex problem because proteins are complex molecules, so a lot of amino acids. And so this complexity is something that scales exponentially from classical computation. Instead, we show that we have a sort of log or linear scaling in the number of qubits with respect to the number of the, let's say, internal structure of the protein itself. I would say that I will stop here for this part. If there are some questions, maybe we can use the remaining part to answer the question. I don't know, Federico, if you have anything else we want to add this part. Maybe I can just share this slide to understand what builds really a quantum workforce for us. So the three main pillars are the open access, so the possibility given to the people to access our quantum platform in terms of software, but in particular in terms of hardware. the open source scenario, so the developing of this KISS-Kit as an open source software where everyone can contribute, and of course education. So we do a lot of education, we do summer school, we help a lot of university providing workshop and some lessons to, let's say, help the students start their journey in quantum computing. Thank you.
Thank you very much. So from what I understand, we cannot solve differential equations, right?
There are some attempts, and there are some preliminary publication on that, because of course it's a very interesting scenario in solving a partial differential equation. But I wouldn't say we cannot do it, but people are looking at it because there's some way to do that. There are, usually we say there are very strong quantum algorithms that are very well known, like HHL, that is an algorithm to solve linear of equation. The problem is that we have to think about what we can do now with this hardware, with this quantum computer that suffer from error. So we don't have at this moment a real quantum error correction. Mm-hmm. So we say that we are using NISQ device, so near intermediate scale device. So intermediate means that we have to deal with errors. So we develop algorithm, but also we need to develop some error correction techniques. And of course, we cannot scale with the number of qubits so much because the quantum volume is not so big to solve HHL algorithm, for example, because those kind of algorithms are very powerful, but they were taught on the paper. That means that they were taught on a theoretical quantum computer. So no errors and infinite number of qubits.
I see.
So that's why we now are using variation algorithms that are very suited for this kind of algorithm. So this is
so the present situation is that basically any sort of minimization and or optimization problem can probably be mapped to this hardware. That's the story?
Yes, I mean, the idea of this hardware is exactly the willing to build a general purpose quantum computer. So this technology can be used to solve a chemical problem, to solve machine learning problem, and to solve optimization problem. That's the only way you can provide a technology that can be used for everyone, for every kind of situation. And that's one of the main differentiating part between our approach and other approach to that. And so, yes, now optimization is very well suited for this technology.
Okay. Thank you. So maybe we should turn to the questions, and I will probably start from some of the questions that were typed before. We have a question that is actually asking two questions. Well, one is, the first part is related to the energy consumption that I think you already said something about that. And the second part is actually asking if the existing codes need to be adapted or modified. And I can probably say, yes, you need to change everything. But I don't know if you want to add something to that while I'm reading the next question.
Yes, maybe I said something before, but the idea is that we cannot do like with the language that I speak in Italian, that I apply some translator and then I speak in Spanish and so on. So there is no translator between classical and quantum algorithm, even if what we are doing with the development of the software is something similar, but because we were able to define new type of algorithm. So the idea is that you have to think completely different because you have to exploit quantum properties. So in principle, you don't translate an algorithm. You have to think from scratch, and then you can apply a sort of transformation.
That's very hard.
Yes.
That's almost impossible.
But that's the funniest part of this.
Yeah. Well, but I would question the word quantum algorithm. An algorithm is an algorithm. There are no classic algorithms for quantum algorithm. I mean, so anyway, so that's part of the story, I guess. Anyway, let's see. There have another question that is actually asking if the qubit, the quantum computer can be used for floating point problems, because the question is that they understand they can use for the logic, so they want to know if it can be used for floating point problems. For instance, when you have to solve a partial differential equation, possibly with stochastic boundary conditions. So I don't know if you want to say something.
But I would say that the part of this floating port, maybe it's not something I know very well, but the idea is that the quantum algorithm should exploit all of the quantum properties during the quantum execution. So another typical problem of quantum algorithm is that they cannot be last so much because we have to keep within the timeline, the lifetime of the qubit. So we cannot store information, we cannot do something intermediate for this reason. So there is no storage concept related to that.
The next question has to do about the criteria to select a specific quantum processor, the one you described. So what are the criteria? What is influencing the decision about how many qubits one needs? What kind of topology has to choose? Are there any sort of guidelines available?
I wouldn't say a guidance, but of course we start with a number of qubits. So it depends on the way you map your problem to quantum algorithm. So once you map your problem, you know how many qubits you need for the computation. And then according to that, you choose different hardware with the same number of qubits. And then the way you choose the right hardware is related to the topology of the qubit. So how many connections you need or how depth is the circuit. And so this is an MP problem. That's why also the compiling part is an open part in terms of research and investment, because you have to solve a complex scenario. So you have number of qubits and then you have number of gates, and you want to position the gate on the right qubit with, let's say, the less depth possible available. And you have to consider the properties of each qubit in terms of single error qubit, but also when you exploit the entanglement, let's say a huge term of, let's say, noise comes from the two qubit gate, which is the C0, which is the gate that creates the entanglement. So
we're really in a very early stage. It's a little bit when we have to put the numbers in the registers one by one with assemblers.
It's not this, I mean, it used to be at the beginning, but now everything, I mean, if you don't want to study this part, everything is done by the compiler. So the software does this for you. So that's already something that is solved. And of course, you can also do yourself. I mean, it's upon your expertise or your willingness to invest time on that.
Then I have a question that is actually asking, what is the capacity in terms of storage of information? And I think we already said that there is no storage, from what I understood. So
yes. There is some theoretical, let's say, proposal that goes back to the 90s, which is QRAM, quantum random access memory. But according to the current technology, we cannot implement it.
Another question is dealing with are all quantum gates conservative logic gates? Can they perform reversible computing? If the qubit represents a point in the sphere and at the end we get 0 or 1, then do we have power leakage during measurements? Based on the measurement result, can we recover the initial qubit state? I have no idea.
Yeah, so quantum computation is a reversible computation. This is one of the main differences with respect to classical computation, of course. But everything, so the magic word of this reversible computation ends when you apply the measurement. So once you apply the measurement, you have the collapse of the wave function. So to some extent, you cannot go back to that moment. And regarding to the power leakage,
that's wave function collapse. That's probably an interesting point.
Yes.
Anyway. Let's see. Next question has to do: would it be possible in the future to use the qubits superposition properties besides classical quantum chemistry applications? For example, could ensemble of clever models be run at once to get the ensemble solution? Similarly, could the machine learning algorithms be trained on the entire training data set in a single probabilistic computation? Oops, who knows? That's the answer. My answer.
Yes.
Yeah. Then somebody is asking to put the information to how to register on your actual in order to access the maybe you can send the website and I'll put it in the chat, or do it yourself. And the last question is actually asking if cosmic rays may actually create a problem for quantum computing.
Oh, I lost the question, sorry.
Oh, sorry. The question is that if cosmic rays can actually be a problem for quantum computing.
There are actually a problem. One of the biggest problems that we have for this quantum computation, apart from thermal excitation, so those qubits are working at 15 millikelvin, so you can understand the complexity of the thermodynamics excitation. And also we have a complex scenario to shield, let's say, the infrastructure from outer electromagnetic waves and also from cosmic rays. And that's why we can access quantum computer via cloud infrastructure, because quantum computers are located inside our data center, because we developed this knowledge in this year. So there is no point now to give a quantum computer to someone external, because that's really a complex scenario.
So you need shielding and isolation from EM and cosmic rays, and
yeah, although the cables are shielded, shielded.
Of course, neutrinos are a problem, but probability is probably low. Anyway, okay. I don't see any other questions, so I'm just asking again if there are some, last moment question.
I put in the reply of the question.
Oh, thank you very much. Thank you.
The link. So.
Perfect.
About the question of Qiskit.org, Qiskit.org regards the open source software framework for Python. In order to access the quantum system, the first thing to do is to register to the link I sent you, which were quantum-computing.ibm.com. Okay. And when you create the account there, you will receive also an API token that you can use inside Python using Qiskit to call your account and then to use the quantum computers. So I think we also answered this question.
Thank you very much. I see somebody is raising its hand. I think Adeshina, you want to ask a question?
Maybe the link is only in the chat. Let me, because someone is asking where is the link. Let me just put it maybe in the general chat. Okay.
Adeshina, you can talk if you want. I don't know why, maybe it's some confusion. Okay, all right, well, thank you very much. I think we were here for an hour and everybody was sticking with us for the entire hour, so that's a major success. So nobody went to have a coffee, so this means it was very interesting. I think this was very informative, very important, and as I said, to me, it's a first step, and I think we will have to continue on this path for long. So I'm looking forward to talk with you guys more and see how we can proceed on this path to try to see if our application can actually be cast on this new technology. So thank you very much and have a nice day to everybody. I thank for all the participants and everybody that asked questions. Thank you.
It was a pleasure.
Bye.
Bye.